My dear students, let me welcome you all to a new edition of physics. In this edition, we'll resume talking about photoelectricity. Photoelectricity is defined as the emission of electrons from the surface of some metals when irradiated by light of certain frequency. Also, it was something very perplexing for scientists, but Einstein managed to explain it. In this edition also we'll learn about Compton effect. So let's get started. Wave-particle duality, photoelectric effect. What about photoelectric effect? It is emission of electrons from some metals when irradiated with electromagnetic radiations of sufficiently high frequency. Your attention please, let me say it again, and you focus on something on the definition, which is sufficiently high frequency. So the effect has to do with the frequency. It is emission of electrons, production of electrons by photons, emission of electrons from some metals when irradiated with electromagnetic radiations of sufficiently high frequency. So we need, yes, a minimum frequency for the phenomenon to take place. As a matter of fact, Einstein tackled the photoelectric effect. In 1905, he saw that all experimental laws could be explained if it was assumed that atom can only absorb light energy in discrete energy packets, quanta. Light quanta are called photons. Photons are indivisible, so each photon gives all its energy to one electron. This is the explanation. So the photon gives its all energy to one electron. Einstein showed that energy per photon of the electromagnetic radiation should be at least equal to the work function of the metal to eject electrons from it. And when a larger photon, a photon with a quantum of energy greater than the work function is supplied, the surplus energy is carried by the electron as kinetic energy. So let's define photoelectricity once again, or photoelectric effect. It is the emission of electrons by light, by photons, when light of certain frequency falls on the metal. Here is something very important. We need at least minimum frequency so as to eject electrons from the surface. Einstein explained this. He said energy of photon, energy of each photon, should be able to eject an electron. So we've got a minimum energy, we call it work function. If the energy of one photon is equal to the work function, it will eject an electron, but its kinetic energy will be, zero. If it is greater than the work function, it will eject electrons, but with kinetic energy. The surplus will be converted into kinetic energy. If the energy per photon is less than the work function, the radiation will not be able to eject any electrons, no matter how intense it is. This was about photoelectricity, and we'll explain it one by one. Einstein explained the effect as follows. If the photon energy determined by H nu, photon energy is equal to H nu, is equal to the work function. Work function equals H nu c. This means that frequency of the photon is equal to the critical frequency or threshold frequency. Okay? If the energy of the photon is equal to the work function of the metal, what happens? The photon energy is just sufficient to eject an electron, and kinetic energy of the freed electron is then 0. Okay. And what about work function? So we need to define, first of all, work function. What about the work function? It is the minimum quantity of energy required, yes, to emit, to extract an electron from a given metal served by just one electron, by a single photon. So let me say it again. It is the minimum quantity of energy required to emit, to extract an electron from a given metal by a photon, by a single photon. The energy that each photon should possess so as to extract an electron. It depends on frequency. So we've got a minimum frequency. We call it threshold frequency or critical frequency or cutoff frequency. And if the photon energy is greater than the work function, this is the second probability. Photon energy is greater than the work function, the electron is freed, and the energy difference, yes, is carried by the electron as kinetic energy. So H nu minus work function, yes, will be converted into kinetic energy, will be carried by the electron as kinetic energy. Okay, so we can say H nu minus work function equals H nu c. Nu c is the threshold frequency or cutoff frequency. Okay, so H is taken as common factor. H is Planck's constant. H between two brackets, nu minus nu c equals half mv squared. Half mv squared is the kinetic energy, where v is the maximum velocity of the photoelectrons, electrons emitted from the surface. Okay, mass of the electron is denoted by small m. And what about frequency? Nu is the frequency of the radiation. Nu c is the threshold frequency or cutoff frequency. And EW, as I said, it is work function. And finally, if the photon energy is less than the work function, the electron will not be freed at all, no matter how intense the light is. Okay, so this was about the explanation of photoelectricity, photoelectric effect. Facts about photoelectric effect. For any metal, electrons are only emitted if the frequency of the incident light is above some threshold value, okay, denoted by nu c. Nu c is the threshold frequency. So weak ultraviolet has greater frequency, high frequency, can emit electrons from zinc, whereas very intense infrared, if we compare between ultraviolet and infrared, frequency of ultraviolet is, yes, much greater than infrared. So weak means, yes, intensity is weak. We've got fewer number of photons, but each photon, yes, is capable of ejecting electrons because it has to do with frequency. So weak ultraviolet can emit electrons from zinc, whereas very intense infrared cannot. Even so, it is delivering far more energy per second to each unit area of zinc surface. Okay? And now we want to define the threshold frequency. Okay, it is also called, yes, critical frequency or cutoff frequency. Threshold frequency, it is the minimum frequency that the incident radiation should possess so as to extract electrons from a metal. It depends on, yes, threshold frequency depends on the metal. Okay. The maximum kinetic energy of the ejected, we are talking about facts of photoelectricity. The maximum kinetic energy of the ejected electrons, of the freed electrons, depends on the frequency of the incident light, incident radiation, and is proportional to the difference between the light frequency and the threshold frequency. Yes, okay. Threshold frequency, it is also called critical or cutoff frequency. What about it? It's high time to define it, okay, to focus on it. It is the lowest frequency of an electromagnetic radiation needed, lowest frequency needed, required to eject electrons from the surface of a certain metal. And now we've got some questions, and we'll together try to solve and answer the questions. What is photoelectric effect? Definition of photoelectricity. It is ejection of electrons of some metals by light of certain frequency. Okay, ejection of electrons of some metals by light of certain frequency. Why does blue light eject electrons from a certain photosensitive surface, whereas red light has no effect on that surface? So we are talking about two lights here, blue and red. Blue has shorter wavelength, has higher frequency, so energy of each photon, energy of each blue photon is greater than the energy of the red photon. Okay, let me say the question again. Why does the blue light eject electrons from a certain photosensitive surface, whereas red light has no effect on that surface? Blue light has higher frequency, that's to say it has more energy per photon. Another question, will bright blue light, okay, bright means we've got many photons. Okay, will bright blue light eject more electrons from a certain photosensitive source than dim light of the same frequency? Yes, of course, because bright blue light has more photons than dim blue light, and each photon is capable of extracting an electron. So once again, yes, because bright blue light has more photons than dim blue light. Another question, in the photoelectric effect, in photoelectricity, does brightness or frequency, brightness has to do with the number of photons, okay, and frequency determines the energy of each photon. In photoelectricity, does brightness or frequency determine the kinetic energy of the ejected electrons? I believe it's all easy for you now. Okay, it is frequency, of course. Frequency determines kinetic energy, whereas brightness, which is intensity, determines number of ejected electrons. Another question, does the photoelectric effect support the particle model or the wave model of light? Let me say the question again. Does the photoelectric effect support the particle model of or the wave model of light? Of course, it supports the particle model. It supports the particle model. Another question. In a photoelectric emission experiment, a metal surface in an evacuated tube was illuminated with monochromatic light of frequency. The frequency is greater than the threshold frequency for such a metal. Okay. If the experiment is repeated with light of the same wavelength but of twice the intensity, what effect will this have on? So we replaced the light with another of the same wavelength, same frequency, but of greater intensity, twice the intensity. Okay, what effect will this have on the photon energy, the maximum kinetic energy of the photoelectrons? Photoelectrons are the electrons emitted from the surface of the metal by light, so we call it photoelectrons. Okay. Also, what effect does this have on the work function of the metal and the photoelectric current intensity of the photoelectric current? We'll take it one by one. Okay. Concerning the photon energy, it will not change. Do you know why? Simply because, yes, energy of the photon depends only on frequency. We didn't change the frequency. Same light, same wavelength, same frequency. So the photon energy is not changed. It's not altered. Okay. And what about the maximum kinetic energy of the photons, of the photoelectrons, of the electrons emitted? Also, it will not change. Why? Simply because it depends on frequency, and frequency is not changed. So maximum kinetic energy of photoelectrons, yes, is not changed. Work function also is not changed. It depends on the metal. We didn't change the metal. And what about the intensity of the photoelectric current? It will be increased. Since intensity of the incident radiation is increased, the intensity of the photoelectric current is increased. Another type of question, a metal surface is illuminated with monochromatic radiation whose frequency is greater than the threshold frequency of the metal. Explain how to increase number of photoelectrons emitted per second. Explain how to increase the maximum kinetic energy of the photoelectrons. Okay, to increase the number of photoelectrons, we have to increase the number of the incident radiation, increasing the brightness of the incident light. Okay, so by increasing the intensity of the incident light, incident radiation, increasing the intensity means increasing the brightness of the incident radiation. Okay, when intensity or brightness is increased, number of photons, incident photons, will be increased. And since each photon is capable of extracting an electron, number of electrons extracted, freed electrons, will be increased. And how to increase the kinetic energy of the freed electrons? Yes, here the light should be replaced by another light of higher frequency. So we have to increase the frequency. We cannot increase the frequency unless we change the type of light. So the light is replaced by another light of higher frequency. The following table illustrates the response of some metals when exposed to different frequencies of electromagnetic radiation. Okay, let me say it again. The following table illustrates the response of some metals when exposed to different frequencies of electromagnetic radiations. Okay, so we've got here a table. We've got different types of metals, zinc, and we used ultraviolet once, then replaced by blue light and red light, and we'll record the response of the metal to each radiation. Okay, ultraviolet managed to extract electrons from zinc. Blue didn't. Also red, of course, did not manage to extract electrons from zinc. So photoelectricity with zinc happens only with the ultraviolet. And what about sodium? Ultraviolet managed to extract, blue managed, red failed. Cesium, ultraviolet of course managed, and blue managed, and red also managed to extract. And this means it's easy to extract electrons from cesium. And what does this mean? It means threshold frequency of cesium is, yes, low, is small. Okay. And what about the questions? Which metal has the greatest work function? It is the most difficult to extract electrons from. Okay. Which metal had the highest threshold frequency? And of course it is which had the greatest work function, of course. Which metal had the longest threshold wavelength? I believe it's all easy for you. So, and which metal had the least work function? We'll take it one by one. Zinc has, of course, zinc has the greatest work function. Okay, it had the greatest threshold frequency, and of course cesium has the minimum work function. It has the lowest threshold frequency, and it has the longest threshold wavelength. So it was in the first case zinc, then cesium and cesium. What's meant by another type of questions? Work function of a photosensitive source is equal to 4 times 10 to the power of negative 19 joule. It means the minimum quantity of energy required to extract an electron from this photosensitive source by a single photon of an electromagnetic radiation is 4 times 10 to the power of negative 19 joule. So minimum energy that each photon should possess to extract an electron is 4 times 10 to the power of negative 19 joule. What's meant by threshold frequency of sodium? 5.6 times 10 power 14 hertz. the minimum frequency of an electromagnetic radiation under which the photoelectric effect for sodium does not occur is 5.6 times 10 to the power of negative 14 Hertz. That's to say, the electromagnetic radiation having frequency lower than 5.6 times 10 power 14 Hertz is unable to extract electrons from the surface of sodium. Okay. What's meant by threshold wavelength of zinc is equal to 310 nanometer. Threshold wavelength of zinc 310 nanometer. The longest wavelength of an electromagnetic radiation above which the photoelectric effect for zinc does not occur is 310 nanometer. Longest wavelength of an electromagnetic radiation above which the photoelectric effect for zinc does not occur is 310 nanometer. And now let's solve some problems. What is the maximum energy and speed of an electron ejected from a sodium surface whose work function equals 2.28 electron volt when illuminated by light of wavelength 410 nanometer, 550 nanometer. Mass of electron is given 9.1 times 10 to the power of negative 31 kilogram. So lambda 1 equals 410 nanometer. It is 410 times 10 power negative 9 to convert from nanometer into meter. H nu 1 equals frequency equals c over lambda, so it is equal h c over lambda 1. H is equal to 6.63 times 10 power negative 34, Planck's constant, of course. Speed of light in space, c, 3 times 10 to the power of 8 over wavelength. It is 410 times 10 power negative 9. It is 4.851 times 10 to the power of negative 19 joules. This is the energy of each photon. Kinetic energy, maximum kinetic energy equals h nu minus EW. EW is the work function. So it is 4.851 times 10 power negative 19 minus 2.28 times 10 times 1.6 times 10 to the power of negative 19. Maximum kinetic energy is 1.2 times 10 to the power of negative 19. Okay, so 1.203 times 10 to the power of negative 19 is equal to half. This energy will be carried as kinetic energy half mv squared. So in this way we can determine the velocity. Mass is given in the problem. We'll do the same for the other wavelengths. The second wavelength is 550 nanometer, 550 times 10 power negative 9 to convert it into meter. Once again, energy of the photon, each photon is determined using the formula hc over lambda 2. H Planck's 6.6 times 10 power negative 34, c is speed of light, and wavelength 550 times 10 power negative 9. So energy of each photon is 3.6 times 10 power negative 19 joule. Okay, work function equals 2.28 electron volt. So it is 2.28 times 1.6 times 10 power negative 19 to convert from electron volt to joule. H nu2 is less than the work function, so no electrons are ejected. And this way we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.